Welcome, folks, to Lecture 13, CS10. Woo! It gives me great pleasure to introduce our guest speaker for today, my colleague Bjorn Hartmann. Bjorn came to us as the hottest, he doesn't know this, so the hottest young HCI researcher in the country. We said we need to really infuse Berkeley's HCI program with the best guy in the country. We did an entire international search. Bjorn was easily the guy that just blew everybody else away. We were so happy when he said yes to Berkeley, and he's been with us for a couple of years now, and he's done some amazing work here. He's going to share some of his history, how he got to Berkeley, which is really inspiring for those of you who are not necessarily computer folks, because he didn't start as a computer person, which is great. And some of the exciting work. He's going to define the entire field of human-computer interaction, which is one of the most exciting fields in the entire field of CS. Without further ado, Bjorn Hartmann, thank you so much.
Great, Dan. Thanks for that intro. All right, now that Dan set the expectations really low for this lecture, let me start off telling you just a little bit about my background. So I went to the University of Pennsylvania in Philadelphia, and I started off as a social science major. I was in communication, and then actually I went into fine arts. And only then a new major came around called digital media design, which had all of that plus computer science. And so I slowly began to move more and more into the engineering direction because I was really fascinated with what you could do with computation. So I ended up getting a master's degree in computer science from UPenn. But then I took a little time out. There was a lot of school in 5.5 years for both the bachelor and the master's. So in my second life, I had a record label. So this is my label partner, Jay Hayes, DJing in Club Milk in Tokyo back in 2003. So we were traveling the globe, DJing. And this is really one of the defining situations that got me into human-computer interaction. So what you see here is, on the right-hand side, the user interface that DJs have been using since the 70s. 2 turntables with vinyl records and a mixer in the middle. On the left-hand side, there's a laptop. What is that laptop doing in the picture? Well, that laptop actually holds all of the music. And the records that are on those turntables don't hold any music. They just have a time code. And that time code gets piped into the laptop, which uses the time code to control playback of MP3 files that then go back to the mixer and out to the speakers. So this was a really kind of a revolution in technology for disc jockeys, because now we didn't have to lug around 100 pounds in 2 cases of vinyl just to play in a club for a night. No, now we could just bring a laptop and have music worth days. So I did that till 2004. And then I made the decision to go to the second best school in the Bay Area and did a PhD in computer science at Stanford University, where I was in the human-computer interaction group. I finished up there in 2009, and since January 2010, I'm now here at UC Berkeley. All right, and here at Berkeley, I teach both the undergraduate and the graduate courses in human-computer interaction. So what is human-computer interaction, or HCI? Well, we can start by just dissecting the term, right? So there are people involved. Those can be the end users of a program, of a piece of software, but there can be more than one, right? I may be interacting through the program with my other friends online. So the humans can both be the end users, but there can also be communities of users that we want to support. Then clearly there's a computer. That's the machine that our software runs on. And nowadays, that's often also not a single computer, but rather a collection of computers. So many servers in the cloud, plus maybe a mobile client that I carry in my pocket. And then we have the interaction part, which you can think of as this dialogue where the user kind of tells the computer what they want done or who they want to communicate with, and the computer processes that and communicates a result back. And it does that through user interfaces. So user interfaces are the part of the application that allows this interaction, this dialogue to happen. And Many of you are familiar with the standard user interfaces, so we have things like menus, widgets, toolbars, pop-up dialogues. But the UI can also include hardware. So think of the Wii mode. A core component of the Nintendo Wii is the fact that there's this hardware controller which has an accelerometer in it, and in the latest version also a gyro that can sense tilt. That is part of the user interface. On the right-hand side here, I'm showing you the Reactable. This is an experimental musical interface. This is basically a synthesizer where you control the quality of the music by moving these physical pucks around a table, and the table also has a display projected from underneath. So HCI, in the larger sense, is the design, the prototyping, the implementation, and the evaluation of user interfaces, whether they're hardware or software. And HCI is really an interdisciplinary field, which is what attracted me to it. And there are three primary strands in HCI. We take the technology part from computer science and electrical engineering. But we take the process by which we go about building good user interfaces mostly from design, so product design, industrial design. These disciplines have come up with a good process how to define products and services that fit the needs of people. And finally, we also borrow from applied psychology, mainly in the methodologies we use to evaluate whether what we designed actually meets its goals. Now, the real reason why I moved into HCI was not that I'm really passionate about those three subjects. That's also true. But more importantly, working in HCI allows me to be one of these four personas on any given day. So if you design, build, implement, and evaluate user interfaces, sometimes you get to be an artist. You get to care about the aesthetic appeal of the user interfaces you create. You also get to be, let's see, which way do we want to go? Well, I'll go to the engineer next, diametrically opposed. I get to be an engineer because I like building systems that work, complex systems that really help people accomplish their task. That is done through engineering principles. Now, I get to be a designer when I try to really think about the fit between engineering and people's needs. So designers contribute methodologies like need finding, where I go out, observe, and interview people about what kind of technology could really meet their needs, for example, for work or for play. And finally, I get to be a scientist where I get to both design, carry out, and then analyze experiments and experimental data to really figure out whether the inventions I came up with meet their stated goals. All right. And the way the design of user interfaces happens is through an iterative design cycle. If you remember one thing about this hour, it's this cycle. This is how user interfaces get built in practice and in research. And that is, we start with a design phase. This is where you come up with ideas. So you ask the question, what should we create? Right? And you may observe people to get some intuition. You come up with a rough design, and then you embody that design in a prototype. So a prototype is something concrete that you can test with your roommates, with target users. That prototype then gets evaluated, and we have different possible ways to evaluate prototypes. And then we use what we learned from the evaluation to reflect on the original design. A, did we succeed in our goals? If not, how should we change the design? And do we need a wholesale redesign of the fundamentals, or did we get the big things right, but the small things are still wrong? So evaluation tells us that. So we go into a next phase of design, build a next prototype that may be more complete, more polished than the earlier one, evaluate that again, and we go through that cycle until we run out of time or budget. And the reason that cycle is necessary is that in anything that any product that touches human users, it's really hard to get it right the first time. And the reason for that is we don't have a complete model of how we as people operate. Right? We know some information from cognitive science. So we know how many different things we can keep in memory before we have to start writing things down and we forget them. We know what kind of color contrasts work better than others. But this is only piecewise knowledge. To really evaluate whether the design as a whole works, we can't just look at it and reason about it in the abstract. We have to embody it in a concrete piece of software, put it in front of people, and test it with them. All right, so let me just walk you through each of these three phases in a little bit more detail. One really important phase is understanding users. So what you do is you go out in the world, you define as who are the people I want to help with my product, and you observe them, and you interview them. You ask them questions. For example, a couple of years ago, I led a course at Stanford, and the task was to find new technology opportunities that improve the life of people at the farmers market in San Francisco. Now, I am not like a vendor at the farmers market, right? I don't know what their job is like. So if I want to design a useful technology for them, I certainly need to find out more about their reality and their needs. So we took a field trip to the ferry building. Now, those observations then lead into the building of scenarios and models, where out of all the rich observations, you try to abstract what are the core principles, the core needs, what's constant across a range of different observations. And those are the principles and the goals for your design. The next step is prototyping. And one of the chief goals in prototyping is just speed. Get something concrete that you can test as fast as possible. So there are a bunch of low-fidelity techniques, such as paper prototyping, where you just draw what your user interface would look like on a piece of paper and have someone simulate using that paper interface. Or you can make video prototypes that look like the real product, but you never wrote a single line of code. It was all done in Photoshop and Illustrator. And there are higher fidelity techniques as well, such as making interactive JavaScript, HTML, or Flash prototypes. The reason we make these prototypes is that the final implementation of something that is robust takes a long time to build and debug. You want to make sure you have your design right and all the design decisions already locked down before you take that big leap into implementation in a systems language. So we take lots of small, cheap, fast steps through prototyping to get perspectives into whether our design is going to work. So some prototyping techniques are, for example, storyboarding, where just like an animator at Pixar, you draw up key scenes of what using your user interface would look like, and then you walk someone through that storyboard. Or you could build a prototype that actually works. This is from the design company IDEO, who created this mock-up of what a digital camera back should look like back when most cameras still used film. Now, this doesn't actually have a lens on the other side, and you can't take it outside because there's a thick cord that kind of connects it to a Power PC, an old Macintosh. But the point is, we can create something like that faster than to ramp up a production line and actually create this camera. This may take someone maybe a week to put this prototype together. But then you can test, what should the screen show? What should the user interface elements be? All right, moving on to evaluation. There are two big categories of evaluation: formative and summative evaluation. Formative evaluation asks the question, are we building the right thing? And what should be different in the next iteration? So you do that early on. Summative evaluation asks, our project is complete. Does it work? Did it achieve its goal? And we have a whole range of different evaluation techniques. Here's a picture of kind of a stereotypical one that is really high fidelity. You have a usability lab where you bring in participants to use your software, and you sit behind a halfway mirror and observe that participant, and all the actions they take are logged through software loggers and video cameras and screen capture. So you get a really detailed account of what happened while people succeeded or struggled with your new software. Is it worth the effort? So one first question is, how much of an application source code is devoted to user interface code on average? Well, this is an empirical question, right? You can just look at existing software projects and count the lines of code that are devoted to the UI versus the back end versus other algorithms. And this is precisely what researchers have done before. So Myers and Rawson did a large-scale study, and they found that in today's applications, back in the 90s, an average of 48% of the code is devoted to the user interface portion. So you guys were spot on. Now, if it's really half of the entire code devoted to the user interface, then probably we should also devote half of our effort in design and testing time to the user interface as well. All right, let's switch tracks a bit, and I want to talk to you for a couple of minutes about the history of human-computer interaction, how we got to where we are today. All right, in prehistoric times, the 1940s, this is at the University of Pennsylvania, where I went to college. ENIAC, one of the first computers, the user interface was a room full of patch cords and knobs and relays. All right, that doesn't look anything like the computers we use today. In fact, here's a photo of the first mouse ever built. This was done by Doug Engelbart and Bill English at Stanford Research International in Menlo Park, right here in the Bay Area. Doug Engelbart was a Berkeley graduate student, and up until recently, he would still regularly visit campus. So this mouse is a little bit different from what you find today in a mouse. Most of the mice today are optical. They have an optical sensor, basically a small camera on the underside. This mouse was electromechanical. There are two wheels, one in the X direction, one in the Y direction. And when you moved the mouse in the Y direction, up the table, the Y wheel would track and the X wheel would scrape. And if you moved it in the X direction, the X wheel would track and the Y wheel would scrape. Here's a view of the bottom just to see those two wheels. And basically, these wheels would then drive shaft encoders that would just relay a signal back to a computer how many units the wheel moved in one direction versus the other. Well, it turns out pen input was actually invented right around the same time as the mouse. Right, Ivan Sutherland, who also had an office in Soda Hall right here at UC Berkeley, did this work as his doctoral dissertation at MIT and Lincoln Labs back in the early 1960s. So I'm just going to show you a quick video of Sketchpad in action.
From the very first movie of Sketchpad, taken in the summer of 1962. So this is 25 years old.
This should look familiar to you, right?
Look at what he's doing. He's pointing at the edges and saying, I want them to be all mutually perpendicular, and Sketchpad just figured out how to do that. Sketchpad is the first system to ever have a window. He's actually drawing on a virtual sheet of paper about a third of a mile on a side.
All right, let's stop it right there, since you've seen this, and this video is also very easily findable online. So what is really, really inspirational here, that within the scope of a single PhD dissertation, Ivan Sutherland basically had the vision for the entire CAD industry and for half the product line that Adobe now sells, right? So there is drawing with a pen. There is constraint satisfaction. So if you're not quite precise, well, an algorithm takes over and makes sides parallel and makes shapes fit. There's panning across infinite windows. Really inspirational. Actually, it turns out one of these design choices is one that we don't see much of these days, and that's the input device. The input device from Ivan Sutherland was the light pen. And the light pen was a pen with a wire that you would just hold up to a vertical CRT, a cathode ray tube, one of the big deep screens. It turns out the light pen has one really big problem. Can anyone guess what that problem is? So there's a question of accuracy. So back then, the light pen actually had a little light sensor in the front, and it would detect when the cathode ray tube would scan by its beam, and then it would say, now, and then it would synchronize that signal with the screen updating logic and figure out the XY coordinate. So because that was really close by, it was reasonably accurate. Yes, we don't use them anymore, but why? Yes. The cost. So back then, these were really expensive. Economies of scale, you could probably make one of these today for about $10. That is a great reason. Yes, we don't use these types of screens anymore. But it turns out there's a non-technical reason why people don't use the light pen. It's not heavy by itself, but it turns out your arm is pretty heavy, and that is exactly the reason. Trying to hold a pen up to a vertical screen for any amount of time gives you a really nice sore arm the next day. And so basically no one really wants to use a light pen for more than 10, 15 minutes at a time. So nowadays we have shifted to tablets and other horizontal surfaces where it's easy to rest your arm while drawing, and that makes a world of a difference. So it just tells you sometimes the reasons why technologies don't succeed have nothing to do with how ready the technology is. They have everything to do with the human factors around it. All right, after the light pen, in the 70s and 80s, we then had the age of personal computing. The killer applications were word processing and spreadsheets, and everyone wanted to have a beige box on their desk. And nowadays, this seems kind of trite, because of course everyone has a desktop. But back then, computers were mainframes that, if you asked really nicely, you would get half an hour of time in the middle of the night. And so the idea of having a computer that belonged solely to you, for your own tasks, was revolutionary at the time. Fast forwarding, you may have heard there was a small announcement earlier on today. Arguably, we've now moved beyond the age where personal computing is the dominant paradigm. And I just want to show you two quick precursors to tablet and mobile computing. Back in 1985, NASA sent one of the first laptops into space. This was called the GridPad. It cost about $10,000 back then, in 1985 dollars. But it was a quantum step about anything that had come before, because it had this clamshell design, which we now still have in our laptops, and it was small enough that you could easily carry it. This was not touch sensitive. However, it didn't take long from the GridPad till we were at a stage where you could go out into a store and buy a phone that had a touch screen that did email and also ran games and other applications. And the first phone that did that was the IBM Simon, sold in 1992. I don't think anyone in this room has ever used one. I've never seen a real one. I don't know, Dan, if you ever had the chance. What the IBM Simon illustrates is actually a really interesting general observation about what user interfaces succeed and fail in the marketplace. Oftentimes, the first iteration has all of the features, but fails miserably because the rest of the world isn't quite ready yet for it. And then 10 years later, someone picks up the same ideas, but by now the technology is affordable enough, it fits into people's lives better, and then it takes off. Now, what is exciting about working as a researcher in human-computer interaction is that we get to play with the technologies at the IBM Simon stage and earlier. So in our labs, we get to play with the technologies that, 10 years from now, you can buy at the Apple Store. All right. If you're interested in history, this is going to be a slide that's going to be online. I have a whole timeline of early user interface kind of landmark events, both in software and hardware, that you can look at. So what has changed from this age of personal computing? What are the research directions that we look at today? Well, here's a quote from Gordon Moore. Does anyone know who Gordon Moore is? I heard mumbling. All right, who's reasonably certain about who Gordon Moore is?
He was a co-founder for Intel.
Yes, co-founder of Intel. All right, so for every ant in the world today, there are 100 transistors. That was in 2003. There are way more than 100 transistors for every ant in the world today. And you could graph this. So these aren't accurate numbers. This is just my rough back-of-the-envelope calculation. Back in the 1960s, when the mouse and the light pen were invented, we had many people per processor. And then in the 80s and 90s, when personal computing came along, we had about one processor per person sitting in that beige box on your desk. And now we've really taken off into this age of what has been called ubiquitous computing, where we have hundreds, thousands, millions of processors per person at our disposal. And you can see these different areas find expression in different types of HCI research. So in the early days, mainframe computing, it was all about human factors. How do we make an efficient interface so one person can get their task done quickly and then let the next person use the mainframe? Personal computing, the age of personal computing was very much concerned with psychology and cognitive science, understanding how the dialogue between one person and one computer happens. Now that we're in the age of ubiquitous computing, there's much more of a focus on what happens when computers don't look like desktop computers and what happens when we use computers to collaborate with each other. So here are a couple of research directions. In the age of personal computing, this was your desktop computer's mental model of you. What do I mean by that? Well, it's how applications thought of our human capabilities. We had one finger for clicking and for hunt and peck typing, 2 ears because of stereo sound, and one eye for one screen. Now, a whole area of research in human-computer interaction asks the question, how can we have computation leverage more of our bodily capabilities? So here are some example projects. This is a PhD project from Dave Merrill at the MIT Media Lab. He now has a startup company called Siftio in San Francisco. And the idea is that we're really good at manipulating objects with our hands. Hand and brain co-evolved. So why don't we try to leverage the dexterity that our hands have better in our computer user interfaces? So instead of giving you one screen that's fixed, his interfaces are spread across many small screens that you can manipulate. So here's a demo video. So there's these games, for example, where you create the maze by moving computational tiles around, or you form words by moving these tiles around. And so each of these tiles is a small computer that has input, output, and that can detect which other computers are near it. Here's another example from another colleague of mine, Scott Saponis at Microsoft Research. Playing Guitar Hero with an air guitar. Well, how does that work? Well, he actually has a number of electrodes glued to his forearm that can sense muscle contractions. And then he uses signal processing algorithms to figure out what the configuration of his hand was given a set of sensor signals. The other really big area of research is to move all the way in the other direction, away from new hardware and sensors into everything that is happening online. So, understanding, modeling social networks is a huge area of research in human-computer interaction. For example, the question, "Are you my friend?" is actually quite complex. What does it mean? Well, it could mean any of these things. Oh, no, there are more reasons. Our social relationships are nuanced and complex. And by conflating all of them and reducing them to a one-bit friend yes or no rating, we run the danger of misrepresenting what our relationships are actually like. And so researchers in HCI both try to understand what happens when we have simplistic models and how to create better models and better algorithms for social networks online. The other part we're trying to understand is online peer production. Systems like Wikipedia, like large collaborative efforts that have really excelled at being now one of the best and most complete repositories of knowledge about our world. And we can ask the question, how does this social participation work in practice? What makes Wikipedia succeed and others fail? And are there any laws or patterns? And it turns out, yes, there are laws and patterns that we can mathematically model and describe. For example, almost any site you look at online will have a so-called zip or power law distribution where the most active users are really, really active, and then the second most active user is half as active, third most active user, yet half, and you have this really long tail of millions of people who contribute very little. And so the question is, if this is the underlying reality, and it turns out to be the reality over and over again, how do we design systems that both leverage really active power users and keep the long tail of other users around, because they still contribute very valuable tidbits, just at a much smaller scale? All right, that is research in the large in HCI, and I thought I'd also tell you about a couple of research projects that are happening here at Berkeley in human-computer interaction. So my own research group does work at the intersection of three different subfields. Crowdsourcing, so collective peer production online, and collective intelligence, design and development tools, that is, new tools and environments for designers and programmers, and work on new types of user interfaces, such as touch-based user interfaces and physical computing, which is a term we use to describe any interface that uses sensing and actuation. And we have a large number of projects across these different areas, too many to kind of survey in the remaining 10 to 15 minutes we have here. So I thought I'd just focus in on two of them. First, let's look at multi-touch applications and toolkits. So most of my projects begin by defining a target user group and a target task these users are trying to achieve, and then finding about what's currently hard, what is not supported, and how technology can help. Here in specific, I looked at how to support co-located design. So if we want to support product designers, I did a bunch of observational studies, and one thing that really jumped out is today there's just this coexistence of physical and digital media in any type of meeting. So this is, in this photo, for example, there are printed out schedules, but then there's also probably a PDF pulled up on the laptop, and someone else will have the group calendar on a tablet. But then things get scribbled down on napkins and into notebooks. And these two worlds live very uneasily next to each other. They basically know nothing about each other. So the research question we asked was, how might we help design team members manage that flow of information across the digital and physical boundaries? And the particular system that we built was a large interactive tabletop display, which looked like this, that allowed you to both interact with digital information because it was projected, so we had multiple projectors showing information, but because it is very large, it's 4 by 6 feet, you can also put standard design notebooks, sketchbooks, other things on that table. So let me show you some of the interactions we then designed around this table. Here, for example, we have multiple people using multiple keyboards and mice simultaneously on the same display. And the users can go back and forth between using keyboard and mouse and touch-based interactions. But I also talked about, what I told you a minute ago, about the motivation that we really wanted to bridge this digital and physical divide. This is all still digital. So let's look at some interactions to bridge that gap. Here you can take your physical design sketchbook, just drop it onto the surface. We recognize where it is, and you just drag off a copy, and a couple seconds later, you have a high-resolution digital copy. You can also go the other way. Start with a digital image, just snap it to your sketchbook so you can trace it, and a minute later, you walk away with a high-quality sketch. So how did we do this? Well, there was a whole bunch of engineering. So we built this table platform by using multiple tile projectors, which project a single unified desktop from the ceiling onto this table. To make the table touch-sensitive, we then put multiple cameras below the table. And these cameras had filters on them that only looked in the infrared spectrum. Then we had a bunch of infrared light sources that would flood the underside of the table with infrared light. And then when a finger would come in contact with the surface, the light would bounce off your finger back into the camera, and you can then apply standard computer vision techniques to find out where that finger is. And you can also find out when you place objects onto the table, right? You also get a reflection, but the reflection has a different shape. So we can now use shape analysis to distinguish between fingers and objects. And that then gives us high-level information, such as right now there's one finger down, there are 3 keyboards down, and 3 mice. And we can track both the position and orientation over time. Now, in addition to creating this hardware, we also work on the software side. So here's a project that a student I co-advised, Kenrick Kin, in the graphics and HCI group, did as an intern at Pixar in Emeryville to support the work that set dressers do at Pixar. So set dressers are part of the animation pipeline. They create the environment that animators later then drop the characters in. So we thought about, if you have multi-touch input, how can you create the right interface for set dressers? And one key insight is when you have multi-touch, you can distribute tasks across multiple hands. So we came up with a gesture set for the specific domain of set dressing. And then we wrote an editor that runs on a multi-touch station that allows set dressers to really rapidly mock up environments that can then be used in a later stage to position characters in, and that then gets sent out to lighting and rendering, and at some later point, an animated movie comes out. All right, so that's some research in multi-touch. We have a couple of minutes, so I wanted to show you one really fun project in the realm of crowdsourcing. So who in the room has heard of Mechanical Turk? Raise your hand. All right, not that many people. So let me take 2 steps back then. Mechanical Turk, this was a chess-playing machine from the 18th century that was a robot that seemingly could beat even good human players at chess. Now, how would they build a robot, a chess-playing robot, back in the 18th century? Well, it turns out it wasn't a robot after all. There was a small person hidden in the cabinet that could look and see, the state of the board, and then with magnets move pieces around. All right, that was the old Mechanical Turk. The new Mechanical Turk is we're seeing a change in the way virtual work happens online. More and more work is happening online. So we now have virtual labor markets like Amazon Mechanical Turk, inspired by the earlier robot, that uses small contributions from people to solve tasks that algorithms can't do on their own. So here are a couple of tasks. For example, you can, for 2 cents, copy text from a business card. Or for $2, manage a calendar. So typical tasks here are things that are really hard for artificial intelligence algorithms nowadays, but that are really easy for almost any person. So image labeling, what's in this image? Spam detection, is this comment from a bot or does it actually contribute to the discussion? Business listing verification, does this business still exist or have they gone out of business? Or OCR, handwriting recognition. This is a really bad quality picture. Can you just type what's written in this picture? Now, right now, online platforms are really good for solving these kinds of tasks that require just basic human cognition. But there's a separate question. What if you have these small tasks that experts can do? Experts right now don't go onto these platforms to, for 5 cents, tell you how to solve a differential equation. They're busy with their jobs. You may have to pay them a lot more. So we had this research question of how can we get expert small tasks done by crowdsourcing? And our idea was maybe we can just leverage local experts, people who are already experts in a particular location. So what's a typical expert task? Well, here's the one that any teacher will understand. Exam grading. Many computer science classes at Berkeley right now have 300, 500, 600 students right now. Grading 600 exams is a daunting task, especially when the exam is written. At the same time, you can't just put this online because people have to have knowledge about computer science principles to be able to grade these exams. So we had the idea to try out peer grading, having students grade other students' exams. What would the incentive be? Well, we thought, can we get students to grade other students' exams in return for snacks? Sounds like a crazy idea. So what we did is we actually found a vending machine, we gutted it, stripped all the analog electronics, and put a touchscreen interface inside. And so you would start by scanning your ID, so we could detect people who try to spam or trick the system. You'd then fill out some questions, and then we'd ask you to grade exams. Well, we showed you the question, we showed you the answer key, and a cropped piece of a scan of someone's image from a handwritten exam. And then you had a slider to assign points. So here's how that would look. So you'd read a question, assign points, submit your answer. You'd now get another credit. And you would work through questions until you had enough credits to then make your selection. And vend your items. So as in other projects, there was a big system building component. So we had some help from a mechanical engineer, and then we used, microcontrollers to control all the vent motors that are in this machine. But all of this building was really to get at a question, and that is this type of grading any good? So for that, we deployed the machine in Soda Hall. And in 1 week, we graded almost 8,000 exam answers for about $200 in candy. So we knew we could get volume. Now can we get quality? And this is once again where we go back to experimental design. How do you construct an experiment to afterwards say with certainty whether your design worked or not? So we defined a gold standard where we hired 11 expert graders to grade the same set of exams. And then we also took that same set of exams and put it online on Mechanical Turk. And that now allows us to compare compared to the gold standard, how good is the machine? How good are online workers? And the answer was, well, this was a 5-point scale. If people chose randomly, expected agreement would be 20%. People online were significantly worse than chance. They were systematically wrong, because that's how exams are written, right? If you don't really know what the question is about, you're going to get it wrong. However, on our machine, we had about 84% agreement with experts, with PhD-level students. Now, the question is, what does that mean? How is that compared to one TA? Well, I told you we took 11 TAs. So now we can analyze redundancy. How good is one TA compared to all 11 TAs? How good are 2 TAs? How good is one person on the vending machine? How good are 3 people on the vending machine? And so the interesting result was, if you added more people on Mechanical Turk, the results just kept getting worse. We just got more noise. However, if you added redundancy on the vending machine, you actually got to be better than a single expert at 30% less cost. All right, these are just 2 projects from a whole raft of a dozen or more. If you're interested, just go to my website, cs.berkeley.edu/Bjorn. And before we wrap up, I just also wanted to tell you, if you're interested in user interface design and human-computer interaction, look at CS160, an upper division course that we teach every single semester, myself, John Canny, and Manish Agarwala. And one last link, we also have an undergrad certificate program. This is the course thread in human-centered design. If you're interested in HCI, we have a whole list of approved courses that are relevant to HCI. And if you take 3 of them, you get a certificate that you can show to employers once you graduate. Thanks.
Let's get Andy Bjorn.